Hi, my name is Carly Stratos, and I'm currently a grade 12 advanced functions student. Today I will be demonstrating how to solve a question from the Nelson Advanced Functions textbook. The question I will be solving is question number 3 on page 542. Recall that the function h of t equals 260 over 1 plus 24 times 0.9 to the power of t models the growth of a sunflower where h of t is the height in centimeters and t is the time in days. A. Calculate the average rate of growth of the sunflower over the first 20 days. B. Determine when the sunflower has grown to half of its maximum height. C. Estimate the instantaneous rate of change in height at the time you found in part B. D. What happens to the instantaneous rate of change in height as the sunflower approaches its maximum height? How does this relate to the shape of the graph? The equation of this particular function, which is h of t equals 260 over 1 plus 24 times 0.9 to the power of t, clearly identifies that it is an example of a logistic function. The general equation of a logistic function is p of t equals c over 1 plus a times b to the power of t, where a is greater than 1, b is between 0 and 1, and c is greater than 1. Upon closer inspection, you can see that the function h of t is the quotient of two functions. The numerator and denominator are two different functions. For explanation's sake, we will call the function in the numerator f of t, and the one in the denominator g of t. Therefore, our function h of t is equal to f of t over g of t. F of t is a constant function because its values remain constant. G of t, on the other hand, is an exponential function. In order to find points on the function h of t to graph it, you must create a chart like this. For any value of t, you must first solve for f of t and g of t individually by plugging that value of t into each equation. Complete the chart. The t values are the x values on the graph, and they each have a corresponding h of t or y value. This knowledge allows you to plot the points on the graph and draw the function. Although this question does not directly ask you to draw a graph, understanding the graph will allow you to better understand the question. Now we can proceed to answer the question. I will reread it to you. Recall that the function h of t equals 260 over 1 plus 24 times 0.9 to the power of t models the growth of a sunflower, where h of t is the height in centimeters and t is the time in days. From this section of the question, it is important to make note of the key components: the equation of the function, the fact that h of t is the height of the sunflower in centimeters, and that t is the time in days. Now, part A instructs us to calculate the average growth of the sunflower over the first 20 days. Therefore, I know that I must calculate the average rate of change from 0 days to 20 days. To do this, I must find the slope of this line. The slope is equal to the line's rise over its run, but we cannot determine the exact value of the rise or the run just by looking at the graph. We can, however, calculate the coordinates of the function at 0 days and at 20 days. Using the coordinates, we can plug the corresponding values into the equation slope equals y2 minus y1 over x2 minus x1 to solve for the average rate of change. Let's get started. The first step is to solve for h of t at 0 days and at 20 days. Since t is equal to the time in days, we must solve for h of 0 and h of 20. h of 0 is equal to 260 over 1 plus 24 times 0.9 to the power of 0. Exponents are solved first, and since 0.9 to the power of 0 is equal to 1, the function simplifies to 260 over 1 plus 24 times 1. When you add the values in the denominator, it becomes 260 over 25, which is equal to 10.4. Therefore, the coordinates of this point are 0, 10.4. Use the same method to solve for h of 20. h of 20 is equal to approximately 66.3631. Remember to keep at least 4 decimal places in rounded values to maintain accuracy. Next, write out your two coordinates. Label 0, 10.4, number 1. Its x value will be x1 and its y value will be y1. The second coordinate's x value will be x2 and its y coordinate is equal to y2. Then, plug these values into the slope equation. Slope is equal to y2 minus y1 over x2 minus x1. It becomes 66.3631 minus 10.4 over 20 minus 0. This is simplified to 55.9631 over 20. The average rate of change is equal to 2.798 centimeters per day. It makes sense that a sunflower would grow around 3 centimeters every day. Since this is an application type question, a sentence answer is necessary. A good sentence answer tells what the solution is and explains what it means. For example, therefore, over the first 20 days, the sunflower grows at an average rate of 2.798 centimeters per day is a good sentence. You have now completed Part A. Part B of this question reads, determine when the sunflower has grown to half of its maximum height. The first step is to determine what the maximum height of the sunflower is. Looking at the graph, it is clear that the flower will reach a maximum height of 260 centimeters. However, if you do not have a graph to refer to, you can still find the maximum height of the function. If you look at the equation, you can see that 260 is the number in the numerator. It is no coincidence that this number is the maximum height. This is the case for all logistic functions. For the function to equal 260, the denominator must equal 1, because 260 divided by 1 is equal to 260. Since the denominator is 1 plus 24 times 0.9 to the power of t, it will equal 1 if 24 times 0.9 to the power of t is equal to 0. 24 times 0.9 to the power of t will equal 0 if 0.9 to the power of t is equal to 0. When a number less than 1 is multiplied by itself, its value becomes closer and closer to 0 each time. Therefore, if 0.9 is raised to a large exponent, its answer would be close to 0. To prove this, I solved for h of 1,000 and it equaled 260. Since Part B asks us to find when the sunflower has grown to half of its maximum height, we must solve for h of t equals 130 centimeters. Therefore, you must plug 130 into the equation of the function and isolate for t. First, multiply both sides by the denominator to get rid of the fraction. Expand 130 into the brackets by multiplying it by every term. Subtract 130 from both sides, and divide both sides by 3,120. Now you are left with the challenge of solving for an unknown exponent. You can do this by changing it to log form. This equation in log form is log base 0.9 to the 0.416666 equals t. This shows how to put a power in logarithmic form. For the power b to the power of x equals c, the log form would be log base b to the c equals x. To plug log base 0.9 to the 0.416666 into your calculator, type log 0.416666 divided by log 0.9. The answer is 30.1636 days. Be sure to conclude with a sentence like, therefore, it will take approximately 30 days for the sunflower to grow to half of its maximum height. Part C of this question says estimate the instantaneous rate of change in height at the time you found in Part B. Therefore, I must find the instantaneous rate of change at 30.1636 days. Solving for instantaneous rate of change, or IROC, is similar to solving for average rate of change, or AROC, as we did in Part A. AROC is the average slope of a function between 2 points. IROC is the slope of a function at one specific point. Since we are finding slope again, we still must use the equation y2 minus y1 over x2 minus x1. However, unlike in Part A, we are not given the coordinates to plug into the equation. We only know one. To solve this problem, we will find the coordinates of a point slightly to the left and one slightly to the right of t equals 30.1636. To do this, we will solve for h of 30.1636 minus 0.001 and h of 30.1636 plus 0.001. You can solve for h of 30.1626 and h of 30.1646 the same way you solved for h of 0 and h of 20 in Part A, by plugging these values into the equation. I calculated that h of 30.1626 was equal to 129.9931 centimeters. Remember to keep 4 decimal places. Therefore, this is one coordinate. Since h of 30.1646 is equal to 130.0068, this is the second coordinate. Label the coordinates as I have done here. Put these values into their designated spots in the equation slope equals y2 minus y1 over x2 minus x1. You will find that the flower grows at an approximate rate of 6.85 centimeters per day. Once again, you must write a sentence answer, such as therefore, at 30.1636 days, the time at which the sunflower is half its maximum height, it is growing at an approximate rate of 6.85 centimeters every day. Last but not least, I will explain to you how to answer part D. It says, what happens to the instantaneous rate of change in height as the sunflower approaches its maximum height? How does this relate to the shape of the graph? This question requires us to investigate and explain what happens to the growth rate as it approaches its maximum height. I would start by finding the instantaneous rate of change of the graph at a day greater than 30. For example, I will solve for IROC on the 100th day using the same method as part C. Step 1. Solve for h of 100 minus 0.001 and h of 100 plus 0.001. This means that you will have to solve for h of 99.999 and h of 100.001. Step 2. Write the coordinates for each value of t and label the values of 1 as x1 and y1 and the values in the second as x2 and y2. Step 3. Plug them into the equation IROC equals y2 minus y1 over x2 minus x1. You will find that the average rate of change on the 100th day is 0 centimeters per day. Now let's take a look at the graph. It is clear that as the function approaches its max height, its slope gradually becomes less steep until it is a horizontal line. This means that the instantaneous rate of change gradually decreases until it is 0 centimeters per day and the sunflower has stopped growing. Now you can answer the question. An acceptable answer would be the instantaneous rate of change in height slows down and eventually comes to 0 as the sunflower approaches its maximum height. This is evident on the graph as the slope of the function gradually becomes less steep and eventually becomes horizontal at the top. And that is how to solve question number 3 on page 542. A career which may require you to solve problems similar to this one would be an evergreen tree farmer. They would need to determine how long it would take for a tree to grow, so that it would be at its maximum height during the holiday season while families are looking to purchase a Christmas tree. That brings me to the end of my tutorial. I hope I have been able to further your understanding of combined functions and the logistic function in particular. Thank you for watching.